Dear panel members and participants from across the world, it gives me immense pleasure today to share with you the highlights of my ongoing research for a more sustainable agriculture. Small island states are the most vulnerable countries faced to the risk of climatic change and pollution. So my presentation today is to highlight the potential of banana fibers as a sustainable resource or material for the development of agricultural mulch to reduce the dependence of plastic mulch in agriculture. I come from Mauritius. It's a very small island in the Indian Ocean. So just look at its small size and you get the idea of how vulnerable it is. Modernization in agriculture has led to an increased consumption of plastic products. Globally, it is even expected to increase by a further 50% by year 2030. Similarly, in Mauritius, the import of plastic products for agriculture and other applications has almost tripled over the past decade. So locally, most of the plastics that are being used in agriculture are for greenhouses and for the flooring, for as mulch in the field for pineapple and strawberries, and for other applications as you can see here. So my focus today is about the low density polyethylene film, which is used as agricultural mulch in the production of pineapple in Mauritius, where we have over 300 hectares under cultivation and almost all the plantations are under plastic mulch. So why is plastics of environmental concern? In fact, use of the plastic in itself is not a problem. It is its disposal after use. Pineapple is it's a long cycle crop. It takes from 1 year to 1.5 years for it to be ready for harvest. So in the meanwhile, the plastics they got weathered and they become brittled and soiled, and such plastics they can't be recycled. So what the growers do, they either burn the plastics or they just they mix it with the soil during land preparation, and with that we get microplastics, and we all know that microplastics are now emerging threats to all the ecosystems. And another concern for Mauritius is that in Mauritius we have a number of regulations on the use of plastics. For the time being, there's no regulations on agricultural plastics, but maybe in the near future there will be. So we have to be ready with alternatives. As mentioned, we have to go towards sustainable alternatives for these low density polyethylene films. So one fast solution would be to just import some biodegradable plastics from abroad and grow and use them. But the problem is that these are more expensive than the low density plastic mulch, and we are importing them, so the cost is going to be much higher. And also in terms of the mechanical properties, they are relatively inferior to the LDPs, and given that they have been mostly tested for short cycle crops, and so they might not be as durable and even suitable for long crop cycles such as pineapple. So a more sustainable approach for small island developing states such as Mauritius would be to develop biodegradable materials from locally available plant biomass. In this way, we are going to reduce dependence on imported products and at the same time valorize the locally available fiber-rich crops, or even valorize agro-waste. We have a number of fiber crops grown on the island, as you can see here in this illustration, and from these we had to select only one for this current study. We also see that the University of Mauritius is focusing a lot on fibers, especially on banana fibers, for several engineering application studies, which led to us to select banana as our source material for our current study. Banana is mostly grown on the island as a fruit crop, and it is mostly the agricultural waste that is left behind after the harvest of the fruit that is of interest to us, especially the leaf, the pseudostem, which is made up of compact layers of leaf sheets. And these pseudostem, they're quite bulky. In the study, we found that 45% to 80% of the whole tree biomass is constitute this pseudostem. And we also determined the lignocellulosic composition, and we found that they had a good composition of cellulose, hemicellulose, and lignin. So out of over 30 varieties available on the island, we retained 8 for a screening. So this selection was based on 3 dimensions, on availability of that variety, and also on genomic composition. So these 8 varieties were uh, were were used for the study. So the leaf sheets were removed from the stem. So the leaf sheets were removed from the stem. The fibers were extracted, and the fibers were subjected to tensile testing. And now, having this mechanical data on the fibers is an important step in the fabrication of the mulch, because we just can't go blindly on fabricating mulch randomly on any fibers. So we characterize the fibers, and based on that, we selected uh, one single variety for the fabrication of the mulch. And so to go ahead with that, we had to bear in mind what we are looking for in that mulch, and which variety would be best suited for us to make that agricultural mulch. So before going ahead in the fabrication of the banana mat, we have to know what's the role being played by the plastic film in the pineapple cultivation, and to which extent will this banana fiber mat uh, offer similar contribution. So so we had some challenges to look into. So first of all, the film that is used as mulch in the pineapple has specific roles. First of all, it suppresses weed. You know, pineapple is a very slow growing crop. Like I said earlier, it takes 1 year to 1.5 years to be ready. So in this process, the weeds can outcompete the pineapple crops, especially in its early stages of development. And pineapple, the variety grown on the island, is quite spiny. So manual weeding can become very difficult. So this plastic mulch, the plastic mulch suppresses the weeds from growing. Also, pineapple cultivation is mostly rain-fed on the island. So the plastics, they retain soil moisture, and they um, keep the soil moist. And also, it is known that the plastic helps to increase the soil temperature, which is favorable for the plants because it reduces the crop cycle. And so here you can see some of the technical specifications of the plastic mulch. So just looking at the thickness and the tensile strength, you can see that they are quite relatively thick and durable and of good strength. So we knew that the banana fiber based mat that we were going to fabricate was not going to be as strong and as durable as the low density polyethylene film, but we had to ensure that it meets the international norms in terms of thickness, in terms of mechanical properties. So by thickness, it should be like around 400 to 700 gram per meter square. Why? Because these mats were going to be pooled in the field for plantation. So if it is weak, it's going to break in the field. So it should be of certain thickness that it can be easily manipulated, and also it can withstand the outside conditions for at least 12 months, because we should not forget that pineapple is a long cycle crop, so the mat should be of a long duration in the field. And also it has to play some similar role as the plastic film, so like retain some moisture to a certain extent, prevent weed from growing, and be permeable to air and water, of course. So to ensure that the final product is uh, sufficiently strong and durable, we have to uh, use appropriate processing technique, and also use the appropriate fibers. Um, so the fibers, first of all, they need to be strong, of course, because fibers with high tensile strength will imply that the overall strength of the final mat will also be strong, and this will contribute to the durability and the integrity of the mat. And the process that we used for the fabrication of the mat was the needle punching method. And so the fibers have to go through several stages of fiber opening, of fiber alignment, and they have to pass through cylinders. So the processing are quite mechanically aggressive, and so the fibers need to be flexible so that they can pass through the cylinders, and they can't without breaking. No, they can just pass through all these stages without any fracture or breaking. Also, for a good mat to be produced, we need a proper networking of the fibers, and this is possible only when the fibers are flexible, so they can easily entangle like between themselves, and produce a continuous and uniform mat. Also, we don't need fibers to be brittle, because brittle fibers will imply that they will be easily prone to break during the processing of the mat making. And also a mat made of stiff fibers would imply that the final product would be relatively weak. So here's the mechanical uh, properties of the 8 varieties. We also have the fiber yield, so the amount of fibers that can be extracted per variety. So as you can see, all these values, they vary largely across the varieties. So now from these 8 varieties, we have to select one best for this study. And because the mechanical properties of the fibers are very important, as I just mentioned, so the tensile strength, the flexibility. So bearing this in mind, these three varieties were retained for further selection, for further evaluation, because you can see the tensile strength of these varieties were very poor. They also had very stiff fibers, because higher values of this young modulus implies stiff fibers. So, uh, so we had these three varieties left, and from this we are going to select one best. So Dwarf Cavendish was retained for the mat making, because it satisfied several criteria of high tensile strength, highest flexibility, low stiffness, and also it is widely cultivated on the island. So this will ensure a regular supply of the raw material. Now, to make the mat, The needle punching non-woven processing technique was adopted, as you can see here. So here's a summary of how the processing was done. So the long fibers were cut into strips of 12 to 15 centimeter length. And here the fibers, you can see they're quite compact to each other. So they were passed through a stage of air blowing where the fibers are made in the individualized, so they're separated, and in this process they are made more aerated, and then they are fed into a carding unit. This carding unit, what it does, it aligns the fibers uh, uh, next to each other. It further makes the fibers more individual, and then this will ensure a proper cohesion of the fibers during this process, and this is how we got a good web. And then this web was passed through this cross lapper, so several layers, and which was then passed through a needle loom where it was punched, and the final product was collected. So in this process of an optimization step, around 25-meter long of fabric, which was 80 centimeter wide, was produced from 10 kilogram of fibers. Uh, the fiber loss also was reduced, because now I'm going to show you some of the challenges that we had. So several challenges were faced during this non-woven processing, and one of the major challenge was the high fiber loss, which was up to 50% during the first stages. This is mostly because banana fibers are known to be stiff. Even though in this study we used the dwarf Cavendish variety, which was selected for its flexibility, even then it is not as flexible as cotton fibers. So a lot of fiber loss was found, but this step was optimized, and then this loss was reduced only to 15%. Also, we had some issues regarding the web formation, so this step also optimized, and then a very good continuous web was obtained. Also, another problem was that often the final product just ruptured, and so a lot of optimization was done at the needle loom stage, and finally the end product, a good end product, was achieved. So the mat was tested, the final mat was tested to see if they are according to certain international norms, and also we set up the experimental plots. So as you can see here, they were successful in setting the plot. Now the plots are growing, and we hope to see the results soon. So in conclusion, I can say that we were able to show that even though banana fibers are known for their stiffness, and we were able to produce 100% non-woven banana mat, and which shows that locally available banana fibers can be potentially used for the development of soil mulches. And in this study, the mulch was successfully pulled in the plantations. They did not rupture, and we successfully established our plantations. So it aligns with all the SDG goals. And so further works would be to evaluate this mat to see how effective it is as a mulch, what are the advantages that it offers to the crop in terms of yield, and of course we need further studies to optimize its quality. And so to end, so thank you very much. Thank you very much, everyone.